mechanical tunneling, or actually wave tunneling in general, wherein we will have blocks which the wave. Do you want to turn it on? Yeah. See, well, now it's going through, huh? How about if we turn it this way? What?
Actually, just using it in this orientation.
Okay.
And then we select the other one.
Yeah, okay, so what we're having here, well, it shouldn't actually come through. We should have total internal reflection at some angle.
If you want total internal reflection, then
yeah.
This way.
Well, total internal reflection would be nothing gets over here.
Right. It's not clear to me this does evidence total internal reflection.
Well, it's pretty quiet here.
Yeah.
Okay. Now, on the other hand, if with the thing there, it's very loud, right? So the beam is coming through.
I actually have another demo to do.
Oh yeah, okay. I think I got it. Okay, this will work. It's a little bit too loud for my taste. Here's the point. What we're trying to do is show how waves can actually. When we taught about total internal reflection, we said that we could begin here. This is as good a place as any. When we talked about total internal reflection, it actually was on the exam, and I'm sure most of you got it. The point was that if you go from try to get out of a dense medium, your beam is reflected at an increased angle. When the angle of refraction into the less dense medium is 90 degrees or greater, the beam is totally internally reflected. This is what we taught you, and I think you saw that in demos, and it's a well-established thing. But there's a little bit of a fine point here. Actually, the wave does not turn around exactly at the surface. It actually leaks out of the surface. Because it's a wave, it's kind of like what we're demonstrating here is the idea of a wave going where it shouldn't be, but it dies out into the region where it should not be. It doesn't stop necessarily right at the surface. So in fact, that is true of electromagnetic waves when they do this total internal reflection, and you say, well, it doesn't appear on this side. Well, it appears a little bit. And it leaks out a little bit before it sort of turns around and comes back. So that is a characteristic of waves where it leaks out. So this is total internal reflection. The point is that if I bring another surface close to it, I may be able to receive that evanescent wave. It's called an evanescent, meaning it's dying out. Evanescent. It's one word for this wave that's just evanescent, dying out like this. But if I bring another surface close, I can actually get it to pick up that surface, and it will propagate more or less straight, it turns out. Now another word for this, see, this is total internal reflection. By bringing this other surface nearby, they've invented the word frustrating. Total internal reflection, because you're preventing the total internal reflection from happening, so they call it frustrated. Now, I really wanted you to see this because it's a very sensitive technique to anything that's on the surface, because anything that's on the surface can interfere with this process. So it's a way, like if you want to see some very thin film or some very small amount of material, if you put it on the surface and you bring this frustrated TIR, you can buy these things. These are instruments, you can actually sort of see things. In fact, you can vary the wavelength or the frequency of the light and sort of pick up the spectrum of the material that's here. Very small amounts, because you're dealing with the light going out about a wavelength. It leaks out into the medium. So for visible light, that's like a few hundred nanometers. So you can get very sensitive detection of materials, thin layers of materials, small amounts at the surface. I just want to see if this works. In other words, right now, looks like let me turn it up. I seem to have hit the total internal reflection. Or I'm turning it way up. That's pretty good right there. Now, so what's happening is the waves are coming through, and they are totally reflecting off the surface. In principle, it should happen that if I bring this sort of pickup thing within a wavelength. Now, the reason we're doing microwaves, it's already working. That's amazing. Is that the wavelength is longer, so this distance is not very small, but rather microwave length. See, if I bring it close, now the wave that leaked out is being picked up by this, and this becomes a sort of simple plane. This is like plate glass. So the wave should more or less go through. You can imagine that at some point when I bring these together, it doesn't even know there's a crack here. So there's some spacing where the wave, the evanescent wave, does not quite reach, and so it stops, more or less, or if I get it out of the way entirely. So this is a very interesting thing, and it's a phenomenon of waves. It'll be true of matter waves, and in matter waves, it's not called frustrated internal reflection, it's called tunneling. Because what they're thinking is that this wave has tunneled through the barrier without damaging the barrier. It's just a wave that's sort of leaking out into the space outside of where it normally should reflect. And then we call it tunneling. And you can frustrate the reflection by, and we'll see with a scanning tunneling microscope, which I'll demonstrate, the way that it's done with a scanning tunneling microscope. Now they use the word tunnel. There, what do you do to get the wave to leak into another medium? It's really the same story. Tunneling microscope, which is another very powerful tool for studying surfaces. What you do is the wave is coming up here, and it's leaking into the barrier. Outside is a metal surface. You bring a very sharp tip, a metal tip, conductor, very close, until you get into the zone where you can pick up the leaking material wave. And you can actually get the electron, just like this wave is traveling through the block, through the space into the next block. You can get the electrons to travel through the gap, which is empty space. Well, it doesn't even have to be a vacuum. It could be air, but it doesn't matter. But it's basically an empty space. And the electron wave will leak through and then continue on its merry way through that conductor. Now, the beauty part of this is that you can make this exquisitely space-sensitive, such that, I will show you, you can actually see, and you'll see why, you can actually see the undulations due to one atom at a time. You can actually see the surface of atoms. And people have used it to look at molecules, similar techniques for molecules like DNA. They've seen actually the shape of it. So, okay, we jumped into that just because James was here to help me get this thing going. I turned the power off and it doesn't stop. Oh, it's because we just figured out how to not conserve energy. I turned the thing off and it still works. Okay, let's patent that one. Turn it off and it has a life of its own. Okay, that's good. Now I'll get back to that a little later, I think. Let's finish up on that if you like. Let me see if I can call up this. Okay. Let's see. No. All right, so let's do this. Let's see if we can get it here. I hope. It was working a minute ago, which proves nothing. Desktop 1. Let's see if this... No. Okay. Should give me something. Well, what it was going to show is they have a little animation of this process. Namely, they allow you by hand to move a tip closer to a surface. It's very, very delicate. As you'll see, maybe we'll do a little of the math on it. And it's you have to bring the tip, as we'll see, to within about an atom's distance away. And that was the technological or engineering difficulty in making this work. Nowadays, you can buy these scanning tunneling microscopes for a couple of $1,000s, and you take them out of the box and they work. This is because it's now 30 years since this was first done, and they've improved the thing so much that it's easy to do. Okay, well, let me go on to some of the things that we're going to talk about. Again, about general properties of waves. I want to make this general. We've talked about these the Schrodinger's picture will be these standing waves. I just talked to you a little bit about here total internal reflection, which can be frustrated, or we sometimes call tunneling. Now, before I go further, let me go back to what we started on last time. That was the Bohr theory. And I did tell you that, or you read it in the book, that the Bohr theory is partly classical and partly something new, really strange things, especially in 1912 when this was done. The new things, well, the classical thing was that you treat the system as just a simple plus charge and minus charge, with the minus charge going around in a circular orbit, and you just do the classical theory of a plus charge with a negative charge. You have the Coulomb force with a little constant k, and one is an E plus and the other is an E minus, so you get minus E squared over the radius squared of that circle, and that force holds the electron in its orbit, which is a force is required mv squared over r, the so-called centripetal force. That's all classical, and that's pretty much it. That's the classical picture of this. But what Bohr did, what was new, was he put in the angular momentum, which is, again, something that we don't talk about terribly much in the course, but it's a very important property. That is, again, let me remind you, it's a mass going around some point with a certain speed. And the angular momentum about that point is given by r, the radius, cross the mv. That's the definition of angular momentum, and it's a vector, and the angle of the direction of the vector is the direction in which this thing is rotating around. So if you take r cross v, we really want to know that it's going around this axis, sort of coming out of the blackboard the way I drew it here, okay? So that's this. So this is a classical concept and important in an object where you have just a single electron going around in an orbit, or you have the sun sitting in a place and the Earth is going around it. It has an angular momentum, and it's a very important quantity because it's conserved. The Earth's angular momentum is a constant. It doesn't depend. Even if the orbit changes in funny ways, you could have a circular orbit and you have an angular momentum, or, in fact, we know that the Earth's orbit is not exactly a circle. It's like a little elliptical. So it's doing, well, this is exaggerated. Here's the sun. We were a little bit not circular, as you know, very slight difference. In fact, odd that in summer we're further away from the sun. That's odd. But the reason we're warmer is not because we're closer to the sun. Of course, this is exaggerated. It's not because we're closer to the sun. It has to do with the angle of the Earth's tilt. That's what makes us warm. So it's odd that we're actually further from the sun in the summertime, it turns out. Curious. But you can have angular momentum like this, and you just keep taking your r and your mv. In other words, when you get close like this, if r gets small, your speed gets higher. That's all, and it keeps the angular momentum. So as you come around the sun, we speed up a little bit, and you slow down when you go further from the sun to keep the angular momentum constant. And this is all classically well known. But what Planck said, not Planck, now we were talking Bohr. Sorry, Bohr. He said that let's say that it's some units of this angular momentum in units of the Planck constant divided by 2 pi. You can say, all right, make the assumption and see what happens. And when you put that in, and the other thing you put in is that unlike the classical picture, what we did not see is the electron radiating as it was going around the nucleus. It was not radiating there in those frequencies. But he says that the frequencies that you will see are due to the change in energy between one orbit and another, divided again by Planck's constant. This is the Einstein relation. So that's the other assumption, which is quantized. It's a quantum idea. Planck's constant appears. Hey, I'm sorry about if you can't see that. I think I can get rid of this for the time being, so maybe you can see better. That blackboard. Now, where can we put this guy? Over here. All right. So these are the new assumptions that Bohr put in. So because out of this assumption that the angular momentum has specific values, it restricts the number of orbits that this thing can possibly take. And you get a formula for the energies in those orbits. And he says that the change is like if you jump from one orbit n to another orbit m over h, that will be the change in energy of the atom will come out as a photon or frequency f. Now, the funny thing is also that in Bohr's picture, let me put it here, these orbits, he says, are what they call stationary, which means they are long-lived, and the electron can sort of live in this orbit, at least for some little bit of time at least, because they can't be perfectly stable, because the electron does jump from one orbit to the other, so it's not perfectly stable. But the electron wants to, we have the feeling that things like to go to the lowest energy state, like if you pour water into a jug, it will go to the bottom, the lowest potential energy. The lowest energy state is down here. It's actually the very lowest is the state where you have one H bar in your angular momentum, and the next one here is 2 h bars. And then the electron will jump from this, well, how shall I say, almost stationary state down to another almost stationary state. And then down to the lowest one, though, this is a breakthrough idea. This is another idea. That one won't radiate because it sense has no place to go. So there is a lowest state that, although in Bohr's picture this electron is going around pretty fast, actually, it's just jiggling. You can actually figure out how fast it's going and what its frequency is going around the thing. It does not radiate. Now, this is another one of those things where he just, sort of like Einstein said, the world is, the experiment is crying out saying it does not radiate. Because if it did, it would collapse into the nucleus and it'd be gone. So he just says, from that state, you don't radiate. It's one of those assumptions. What can you do? And it apparently is true because we're all here. You know, if all our hydrogen atoms collapse and all our other atoms collapsed, we just simply wouldn't be here. Yes? We'll get into that in a second. Yes, they had the same basic pattern, but they're more complicated. He picked the easiest case, and he got it right up to this point. We'll see that when you do it a little better with the way Schrödinger did it, it allows you to elaborate the theory in a more satisfying way. But Bohr has tried as hard as he could from 1912 to 1925. He tried to see, could he do the next atom, helium? Couldn't do it. Try as he may, he couldn't get it, and no less the even more complicated ones. This theory just doesn't extend very well. And we'll see why. When Schrödinger came along in 1925, 26, his theory allowed for other atoms, but there's a resemblance. It's kind of a resemblance of the wave mechanical Schrödinger picture to this, in that there are kind of orbits, shells as we call them, and they do have angular momentum going from, well, Schrödinger would say you don't start with 1, Schrödinger starts with 0. We'll see. Schrödinger starts with 0 and goes 0, angular momentum 0, 1, 2, 3. Bohr started with angular momentum 1, 2, 3, 4. That's a difference, but it's not colossal difference. But you can see in Schrödinger's picture the fuzzed out version of Bohr. But I wanted to make sure you understood what Bohr's model looked like. If you actually put it in, when you calculate it all out, that you get the, where shall I put it? Let me put it over here. You get the energy of each of these states. The nth state is given by basically minus this famous number, minus 13.6 electron volts. That's the lowest energy state. So I've drawn the picture here. So the electron sits in its lowest state. Let me maybe make a different color. About here. This is the n equals 1 state at minus 13.6 electron volts. You can multiply the electron charge times 1 volt and you get how much energy that is. It's not much, but for an atom, it's quite a bit. Okay, but the nth state, you divide by n squared, it turns out. So that, let me actually draw these in. So for n equals 1, you get minus 13.6. For n equals 2, you have to divide that by 4. 4 into 13.6 comes out roughly, do I have it here? Yeah. Minus, well, 4 into 13 is roughly 3. 4 times 3 is 12. So the next level is at minus 3.4, which is roughly here. So that's the n equals 2 level at the energy of minus 3.4. Okay, let me put the energies over here, minus 13.6. So you see there's a pretty big gap between the first level and the second. And the third level, you divide that by 3 squared is 9. 9 into 13 gives you roughly 1.5. So that's roughly here, minus 1.5. And the next level is n equals 4. This is n equals 3. n equals 4, you divide that by 16, so you can get something a little less than 1. It's 0.83. Okay, so we have n equals 4. Maybe that's enough. And then they get closer and closer together. N equals 5, you divide that by 25, and you get something or other, but I didn't write it down. So now let's see how this plays out for the spectrum of hydrogen. So on Bohr's picture, so what the experiment you do, and you're doing it in the lab, I think, this week, is that you take the light from hydrogen and you shine it on a diffraction grating, and you put your eye over here, and you see the light coming from that, diffracted from this grating at a certain angle. And we have the formula already, n lambda is d sine theta. And let's just work in the first order. That means that the first full wavelength gives you a peak. So you get that the wavelength is proportional to the sine of theta. So I'm going to draw the spectrum with, so the bigger the angle, the longer the wavelength, the shorter the energy, the smaller the energy. So if here's theta, so let's see what is the, let's pick some wavelength. Let's start with the short wavelengths. So my wavelengths are, how shall I do this? So I got lambda is d sine theta. So the bigger the angle, the longer the wavelength. So this is long wavelength. And the frequency is going this way. Shorter wavelength will be higher frequency. So this is, in a way, an energy scale. Is that right? Am I right on that? The bigger the angle, the longer the wavelength. And so, yeah, I'd like it this way because I'd like to plot things as a function of energy frequency. So let's see what this means. The longest wavelength that I'm going to talk about is the ones that arise from the smallest energy. So let me try the level where things end up in level 3. Maybe I should draw that over here. Here's level 3, and here's level 4. Overwriting myself here. Let's just extend this graph. Here's level 3, here's level 4, here's level 2, and level 1 is over here. Now, the longest wavelengths are from like level 4 to level 3. There's one like that. And of course, there is a level 5 up here, a little closer together. Of course, that's divided by 25. So you have an energy change like that, which gives rise to a spectral line over here at long wavelengths and another spectral line over here. Due to the transition, what's key is where the electron ends up. If it ends up in level 3, the final state is 3, you get a bunch of lines over here, and their energy is relatively small. You'll see compared to those that end up in level 2. Level 2 is over here, and the light that comes out is light from electrons dropping from level 3, for example, to level 2, and from level 4 to level 2, and level 5 to level 2. So you get a bunch of lines over here. Here, here, and closer. And the ultimate one is if this is when the electron is actually free, you can actually knock it out of the atom and it will be a free electron up here. That's called the ionization limit. That's when you ionize the electron, so it's off the atom entirely. There is the limit. That's the highest frequency that you can get for that group. So there is what's called the series limit. This is the limit. Because that electron is dropped from very near being ionized down to level 3. And you get a series limit in this fellow too, also, that is to say, from the ionization down to here, and you get a series limit of this group. So you'll have a bunch of lines in here which are ending in n final equals 2. Okay? And then we get the group where you end up in level number 1. So those are, let me do it in yellow. That'll be from level 2 down to level 1. Now look at that guy. And here you have level 3 ending up in level 1, and level 4 ending in level 1. And then you have the series limit. The guy starts out pretty much ionized and comes down to level 1. So that's the kind of spectrum that'll come out of hydrogen. Now, as you can see, because of this square thing down here, these levels are separated by quite a bit here, so that, in fact, in your lab, you will be looking at this group here. This group happens to turn out to be in the visible, the wavelengths of those that we can see with our eyes. This group here turns out to be in the infrared, and we can't see them, so you need special gratings would be easier because the wavelength is longer, but you need a tool to detect them. And these are named after the people that first sort of measured them. This one is called Paschen. The one we are most familiar with, and you're going to work with, was analyzed by the man Balmer, who sort of understood this series with the visible because he could understand this thing. And this series here was done by, I think, a professor at Harvard named Lyman. I think there's a Lyman lab at Harvard, if I'm not mistaken. So he was the one that. Now these are in the this is in the ultraviolet. So again, we can't see them, and also the wavelength is shorter, so you have to make a better grating with smaller d because the wavelength is small. So that's pretty hard to measure this thing too. But the important thing is that you have this distinct grouping of a bunch of lines here in the infrared, and there's a big spacing and littler spacing in between, and then there's a limit. Then you have a group in the visible with a big spacing because of the squaring under there, big spacing, little, and an end. And then you have, in the case of the ultraviolet, a big spacing, little, and an end. So there's this uniform pattern that they saw. And all of this gets explained by the Bohr theory. It's quite wonderful as far as it went. Okay? And I wanted you to see the whole picture. In fact, you can extend this up. If you go to heavier atoms, you'll see the same pattern, but the wavelength keeps going up and up. Not the wavelength. The frequency goes going up and up into the X-ray region. And you'll see the same pattern of transitions in the X-ray region. Yes?
So if the energy has come to the electron, and doesn't quite correspond to the levels, does the electron still get excited? And it still jump?
Well, yeah. The way you want to think about it, actually, you lead me to a very good point. How do the electrons jump and that sort of thing? The point is that you want to think of these levels as shelves where the electrons can live, at least temporarily, shelves. And they can drop from one shelf to another. Now, the very important point, going back to a Planck idea, namely that if an energy level is too high, there'll be no occupancy of that energy level. So you need, here's the point. Okay, I have to do some erasing just for fun. You lead me to a good point that a lot of people leave out when they talk about this, and that is that how does an electron jump down if it didn't get up in the first place? In other words, you have these energy levels, but at a limit. But we're talking about the emission, and you're going to be working with the emission in the lab. You're going to put the reason you can get an emission. Here, let's look at this. Between the lowest level, 13.6, and the next level, 3.4, is roughly 10 electron volts. 13.6 to 3 minus 3. So the difference here is approximately 10 electron volts. It's very important to realize on this scale, it's a big number. Now, the point is, as Planck said, if you have an energy gap like this, the system will not get into the excited state unless you give it some energy to go all the way up. It doesn't absorb if you just give it a little bit. In the case of vibrating molecules, we had KT was the way, it's kind of fuzzy excitation, KT. Now it's different K. It's not the same K as over there or over here. That's Boltzmann's constant. So this is a thermal energy. If you give enough thermal energy, in other words, like this, that's the energy gap. If your KT is the order of that energy, the particle can get up to this state, right? Otherwise, it doesn't have enough energy to get there. Okay. Now, so the question is, in a hydrogen atom, are there any electrons in the state 2? Here's state 1, here's state 2. Well, what is KT at room temperature? It turns out that this is a rather important idea. KBT at room temperature is about 1/40th of an electron volt. You just multiply the Boltzmann's constant by 300 Kelvin, and you get about a 40th. And so what we have in the case of the hydrogen atom, we don't have nearly enough energy to put an electron in the first excited state at room temperature. At room temperature, you got a 40th. This is in hydrogen, it's 10 eV. We have a 40th. So we're off by a factor of 400. And it turns out that it goes into an exponential. So you get the energy over KT. The energy you need is 10 eV. What you have is a 40th. So you're off by a factor of you're off by e to the minus 400. Which means e to the minus 400 is like, means zero. It means you probably won't get an electron in that orbit in the lifetime of the universe because it's so frozen out. So what you have to do in order to do your experiment and see these things, you've got to put enough energy into this high hydrogen. Well, the whole story, if you can get 13.6, you can get them way up there. If you put in 13 volts, you get them way up there. And you do that electrically in your experiment in the lab. You're going to put an electrical discharge through here. That's going to give at least 13 volts to this. Then your electrons get up here, and they cascade down. And you get all of these lines. If you put them up here, you're going to get this line and that line and that line. But you're going to get all these, the ones that we're interested in are the ones you're going to see are the ones that end up in this level here, the Balmer series. They're going to come cascading down, radiating all kinds of frequencies which you won't see. The ones you will see are the ones where they happen to end up in n equals 2. And they will give you visible lines. You'll see these visible lines. So that's in emission. But you see, in absorption, you have a different world. If you try to shine light through the hydrogen gas, then you see you're starting out with the story. How much time? Oh my God, time is gone. You're starting out with the story. All the electrons are in the ground state. And if you shine light into here, you won't see any absorption. What you'll see is that light would be absorbed to the n equals 2 and n equals 3. So you'll see a certain absorption lines, but you won't see this kind of thing. You won't see that frequency being absorbed because there's nobody there. There's nobody there at room temperature, which goes to the whole other story of how lasers work. This may be a jump in your mind. But to make a laser work, what you do, if you want this frequency from a laser, what you do, you start out with the system in this ground state, this we call the ground state, and you pump with a very strong energy of some sort, usually light. Yes, usually light, sometimes electric. Oh, the little laser that I showed you last time, that was pumped electrically, sort of the way you're going to work. What do you do? We put in an electrical discharge, which put the electrons into a high state, and they trickle down to some state like this one, where they will sit for a little while, and what happens then is if one of them drops down from here to here, they're trickling down. If one of them drops, it emits a photon. If there are more electrons populating these states, different atoms sitting in this state because they've trickled down here and they're waiting, they're sitting, semi-stationary, how shall I say, long, then that photon trips this one and makes it release its energy by dropping down, and it emits a photon in step with the first one. Those two trip this one, called stimulated emission, and cause now 3 photons in step to become a two. So that's the theory of the laser. I have to tell you, I have 2 minutes of this time for one more joke, and that is, sorry we didn't get to Schrodinger, but laser is the acronym laser. I think I said this before, is a light amplification by stimulated emission of radiation, okay? Now, actually, this is a slight misnomer, because an amplifier, what the word means is it amplifies, it makes things bigger, right? That's what you have in your radio. Your radio picks up a weak signal from far away, and you put it in the radio, and the radio amplifies it and makes it big enough for you to hear. It's very weak to start with, if you amplify it many times. But an amplifier starts out with something from elsewhere, and you just make it bigger. Now, an oscillator, on the other hand, it starts out with nothing's coming from the outside. It creates its own wave, right? An oscillator, like this thing here. We don't put any waves into this. This is a klystron. This is an oscillator, a generator. It generates its own waves by some trick. So that's an oscillator. So this actually, a laser is really a laser oscillator, light oscillator is really what it is, oscillator, by stimulated emission of radiation. But this is but they don't want to call it that. Of course, that would be very discouraging if you called it a loser. So I don't know if that's why they stuck with light amplifier, but it really is a loser. I mean, it's it's turned out to be a winner in the right sense, because they're all over the place now, right? Your checkout counters and your lasers everywhere. But that happens to be true. And it's nice to know actually the difference between an oscillator and an amplifier, just in general. And that's the funny story. I really hope to get on to solid today. I'm nowhere near it. So we'll have to begin. Oh, my God, the worst thing. Today is, tomorrow is Planck's birthday. Oh, my God. So let me, where is Planck? Max Planck, as a young man. He was, of course, was the originator of the quantum theory. In his later years, he looks rather sad. He had a rather sad life. I think he had 2 daughters who died, one in childbirth, another, and he had a son who was involved in the plot to kill Hitler in 1944. And of course, the plot failed, and all the conspirators, including Planck's son, were caught, and he was executed. But Planck was in Germany all that time. He didn't support the Nazis. Obviously, apparently his family didn't either, but they left him alone for some reason. The Nazis did, and even after his son was caught. And he lived through the war and died in 1947, highly respected. And to this day, he's honored in Germany because you have what's called Max Planck Institutes. If you ever go to Germany to study, you'll probably end up in a Max Planck Institute because he's clean, he was brilliant, kind, and a good man. So we have a birthday party, of course, German cookies. Also in honor of, de Broglie, we have some French cookies. Please come up and let's snarf before you go to class. Here's some German cookies in honor of Planck and Leibniz, a great man. So, and oh, yes, of course, Newton's. So let's eat.